Hi, my name is Nicholas Wiley. This is part 4 of homework 1 for material and energy balances. What we're going to be looking at is a closed system problem. Now the problem statement that we have is an open container initially at 1 atmosphere and 298 Kelvin contains 1 kilogram of liquid water. The container is sealed without removing the air, then heated to a pressure of 2 bar, at which point the vapor space contains 0.3 moles of water. What is the final temperature and what is the total volume of the container? Now before we begin, Carlos, I have these notes right here. It basically just states all of the knowns and then some equations later on I'll tell you, and there will be a picture of this at the end, but no, I didn't write the code on paper, I promise. All right. So here we have the diagram, got a little bit cut off, but we have the reds are the unknown, the total volume, and the final temperature. And then we have all of our knowns right here. The initial pressure, the initial temperature, the final pressure, the mass of the water in total, and the moles of water vapor. And then also through the key tools, I want to say chem tools. The chem tools we know, all of these values, not really these two, but we can calculate them very easily using those chem tools. And also we have the R value written down. So here we are, you can see the diagram a little better. Also, we know the mass of water vapor. It is right here. So, what I have done on the left side is I have listed all of the applicable variables for this problem. R is not included as it's a constant. So what we have is we have the two desireds, actually I'm not going to use the word desired, the two goals. We have the final temperature, we have the volume total. We also have 7 knowns and 7 unknowns, which I thought was quite peculiar. I mean, there's an even number of knowns and unknowns when I listed them out, which I was like, okay, that's pretty cool. So my main goal with writing all of these right here, was I was going for the totals. So the volume, the total volume, the total pressure, I guess the final pressure, and also rearranging PV equals nRT, just trying to use all of these to build as many relationships as possible. So first off, we had the total volume equals the volume of the liquid plus the volume of the vapor. Pretty straightforward, just looking for the total, its components. Same here, we have the mass of the water total equals the mass of the water vapor plus the mass of the liquid water. So another just summing it up. Again, here the final pressure is equal to the pressure of the air, which does not change through, we have the final pressure here, the pressure equals the pressure of the air plus the pressure of the water in the end. And then we have the pressure of air equals this, so we're just bringing this down here, equals the moles of air times R times TF over V vapor, just rearranging PV equals nRT. We have the volume of the liquid equals these two values right here, mass of the all the water and also the mass of the water vapor over the rho W at final temperature. So what this is doing is it's pretty much just the volume of the liquid equals the mass of the water, which is the total subtracted from the vapor, so the mass of the water over the final density of the water. So that'll give you the volume. I thought that this number 6 equation was pretty cool because when you first looked at it, like right here, it's like, okay, there's 2 unknowns, but then once you start to like take in all these other equations, you realize you know everything here except for one thing, the total volume. You know all of this because the moles of air does not change. The air that was in there originally is not escaping. There's not more coming in. It is constant. So what you can do is you know that the initial pressure minus the initial pressure of water, which is found using the Antoine equation. You can use initials only for this one right here. My mouse just disappeared. Let me get a pointer real quick. So you know that since no gas escaping or entering, you know that the initials you can use to figure out the moles of air. So then you have the volume of the vapor, which we had like up here, pretty much equals the total volume minus the volume of the liquid water. And the volume of the liquid water is actually just the, the mass of the water liquid, obviously, over the density initially at the initial temperatures here. So, okay, that's more knowns. And then you also know the initial temperature and R. So this one is going to be very helpful for us. And then lastly, we have the moles of the water vapor equals, just again, PV equals nRT, rearranging. All right, so what are we going to do from here? First off, I'm taking your suggestion, and what I'm going to do is I'm going to solve the final temperature and the volume total, duh. But to do this, I'm going to drive two of our knowns to 0 with roots, using these two as our the basis of our function, which we are going to create in Collaboratory. And a big thing is we need two equations for the two unknowns. That's the big thing, right? So it's a little bit cut off here, but again, I listed these seven, pretty much, yeah, same order. I listed these 7, 1 to 7, because I found it very peculiar. There were 7 unknowns, 7 knowns. So I just made an equation for each one of these so that we could build relationships between everything. And then once we do that, we're going to be able to find, we'll just see in the code. I hope you know what I'm trying to say, but we're trying to build relationships between all of these to lead us to here. All right, so first we have the moles of air. This is just taken from the last slide. The mass of the liquid water, just reorganizing. And also, instead of using the mass of the water vapor as I did in the last slide, as I'll explain shortly, I included the conversion to kilograms from moles. And then we have, I'm just going down here. So then we have the volume of the liquid equals the mass of the water liquid. Again, it's black because technically we don't know. We do, but you'll see why. And then we have the density of the water at the final temperature. Again, density formula reorganized. And then here we have the volume of the vapor. So I wrote that one down. Just again, simple reorganizing. And the pressure of the air right here. Now the last two, I'll just move to the next slide. They're easier to see. So the next two right here I didn't include because they're pretty much, we're going to use the chem tools and just use the pressure as a function of the temperature and then the density as a function of the final temperature. So the big thing up here is that we want to drive these two values to 0. We couldn't really we could drive other values to 0, I guess, but you did it this way, so I'm also going to do it this way. So what we're going to do is we want to change TF and V total. We want to try and get these to the correct value so that they correlate with all of our known values. So by using the desireds for final pressure and moles of water vapor in unison with their known values, and a function of these two unknowns with everything contained inside, all of these equations contained inside of the function of these two. We can change the unknowns according to minimizing the difference between the desireds and the desired numbers and their true actual constant number. We're going to do so by using a root function. And again, on here I have it written down. This is just all of those 7 equations you see on the left. And again, just reorganizing the final pressure. And instead of volume of vapor, that's wrong. That should be pressure of water. And then this is just, again, PV equals nRT being rearranged. All right, so, and here's the sheet. You can compare. Now it's time for the fun parts, and I hope that I can do this correctly. So I have this to start. I hope it's not too upsetting for you, but I just thought I'd put these in to save a couple minutes. All right, so first, what we're gonna do is we're gonna create objects out of, I forget the exact terminology you told us, but I know that what I need to do is p dot. So pretty much we're going to take the properties from those we're going to take those chem tools, and from there we're going to take the property. We're going to take the property of water, which is the big part of what we're doing, and then we are going to Oh, so we have that final pressure. So we are actually going to do the PFD is the pressure desired, and we're going to make that our constant value instead of just the final pressure. So we're going to do, I believe it's 2E5, and then we will do the same for the moles of water vapor equals, is it 0.3? 0.3. All right, and then next, what are some others? We have R, so 8.34. We also have, and I remember you told me to do this, or told all of us to do this, 101. Add the period at the end for flow. Oh. And then we also have the mass of water total equals 1 point. And I believe that that is it for that section. And I think that we're ready to start putting. Oh, that's embarrassing. Okay, I think we're good then. All right, so this is where it gets fun. So I know that we need to define equation. Did we use v at all? Vector. Man, this is going to be tough. Carlos, I haven't done too much coding in my time, so I'm going to do my best. So we're going to do the final temperature and the V tot. I'm going to have to remember. Here, all right, and now we start building. So, oh, also what I was going to do, I'm going to add something here. So pressure of water initial equals P dot, what is our initial temperature? 290. Oh, I didn't even add that. Is there anything else? I think I'm good. Yeah, I'm good now. All right. So now we have all this. That should work. All right, now let's move on. The first thing we need to do, we have the PWI, we'll do PWF equals, so this will be the first one. This will be, what's vapor pressure? Oh, there we go. Now, as I said, we're building this function, this vector right here, around these two to begin with. But what we're going to do is we're going to solve these according to driving those desireds to 0. So now we have that. And do we need any other equations? I guess we'll start with my favorite equation, the one that, the Nair one. Yeah, we'll do that. So we have equals going to multiply that by the total volume, which we don't know, minus mass mass of water. I'm sorry I'm really slow, Carlos. I'm just going to give you a heads up. I'm really sorry. And then the density of water. Oh, that's the... This is the rho WI. Oh, that's going to be annoying. Let's do it. I'm going to have all of this divided by R times T. That looks correct. Now, after the moles of air, we can do the mass of the liquid water. Mass of water total minus, and like I said, we're going to be using the desireds instead. I think PEMDAS should make this okay. I hope that that works. I actually haven't ran this yet, so hopefully this is a successful attempt. Let's keep all those on the same line. Now, next up we have the volume of the liquid water. Just volume of liquid. What we're gonna have the mass of the liquid water divided by the This is the density. Why did it do that? And the liquid, okay. Next we have the volume of the vapor, and again I'm just going down the line of what I had written down from 1 to 5 for the 7 unknowns but not goal variables. So we have V vapor equals V tot minus volume of the liquid. I hope I'm keeping up with my variables correctly. And then after that we have the pressure of air. This is a big one, so I'm gonna, not a big one, but and I think that this should be fine due to PEMDAS, like your son says. I remember you saying that. So we're just going down the equation once again. Oh, and then, okay, this is where I should probably start explaining. So we have these relationships here. These are what we've built up, right? And now what we're going to do is we're going to set up the, driving these two to 0 with their, so these are the true values. We're going to end up doing the, making, why, I'm just going brain fart. We're running equations for these so that we can change these values in order, we're going to drive these to 0 in order to get them to as close as these. And by doing that, we are simultaneously changing these two right here. So in the end, what we're going to get these two values, but we also have to change these two values, which I'm about to write, the PF and the moles of water vapor. We have to change those two and drive them to 0 in order to get us to our goal. I hope that made sense. So now we have the P air. Oh, I hope I didn't make any issues up there. Oh, yes, I did. Why didn't you tell me, Carlos? PF. Do I have any PFs in here? PFs. Do not P air. I feel like I'm gonna have so many errors at the end of this. I really hope I don't. And then again, we'll do the. We're gonna come up with the what we're going to relate the true values to for the moles of water vapor, PV equals nRT. So we're gonna have PWF times VVAP divided by now this all looks pretty good following my equations. So we've gotten all of these equations down. Now what we need to do is we need to get ready for the return function. And what the return function is going to do is it is going to return these values. Here, I'll explain it in the end. It'll be a lot easier. I just need to get this done with. So we're going to start with P minus P F. And then we're also going to do, this is how you do it, Carlos. So I'm copying you. D minus W. Please work. Troubleshooting. So instead of this, what we're going to do is we're going to do P dot PVAP at TI. And then what else we got? RWI, that's okay. V total, that should be okay. Troubleshooting. Oh, I need the. Oh, did it work? I know I should be surprised. I'm sorry, but okay. Okay, so now what we've done is we are finding these. It's going to return these values to us. And what we're going to do is we are going to root. I can't believe I did this. The equations according to some guesstimate values, which I took from you. I believe it's 350 and 0.2.